So in today's video, we will discuss about the magnification of a telescope, an astronomical telescope. For that, we have two lenses for a telescope. One will be the objective. This one is objective. Objective is the lens which is positioned close to the object. And let this be its optic center. And let me draw a principal axis through this optic center like this. Okay, see, since we are dealing with telescope, we have objects at very large distances, that is at infinite distances. This AB may be a planet or a star or something like that. So rays are coming from infinity. So any ray which comes from infinity are always parallel rays like this. Okay, let me draw a mean line through this optic center so that I can take all the refractions about this line. Okay, but we know any line or any ray which passes through the optic center passes undeviated like this. But the ray which is not through the optic center or slightly above the optic center, after refraction passes like this. Clearly we know from the principle of this convex lens, objective is a convex lens. See, it has focal length of FO, which is a higher focal length. Also its aperture is high because it has to gather more light. So any ray coming from infinity or the image of this object is always formed at the focus of the objective. See, this is the image formed and this will be the focus of the objective. Clear? Now we have one more lens called the eyepiece, that is another convex lens. That is called the eyepiece. Eyepiece, which is having a focal length FE, and the focal length of eyepiece is less than focal length of the objective. Also, its aperture is also small. Okay, so this is the direction of the rays coming from the infinity, from an object which is at infinity. Now the function of this objective, this part you listen carefully, this objective has a particular function, because this image formed by this objective should be within the focal length of this eyepiece. So the focal length of the eyepiece should be, or the focus of the eyepiece should be somewhere here, so that this image is formed within the focal length of this eyepiece. Clearly at the same distance, let us mark this point as some O dash, that is optic center, and at the same distance, that is FE O dash, there will be another focus here also. Let's mark that. Let's mark this as FE dash and this be FE. Now again, taking the principle, any ray passing parallel to the principal axis like this passes through the focus like this. Okay, any ray passing parallel to the principal axis, that is, this ray is parallel to the principal axis. So it will pass through the focus like this. Now I have to take one more ray. This time I'm taking a ray through the optic center. And we know any ray through the optic center passes undeviated. Okay, this will be a straight line. Okay. Now we have these two rays are diverging at this point. Clearly we are looking through the eyepiece our eyes will be here. Clearly, in this side of the eyepiece, these two rays won't meet. So when I extrapolate it into other side, that is these two rays, clearly I get a virtual image in here. So this is the final image. Let's call this as some A dash B dash. So this will be our final image, A double dash B double dash. Clear? So this is the image formation in an telescope. Okay. Now we know we have the magnification. We need to find the magnification. And we know by definition magnification M is equal to, see, before that I have to define two angles, alpha and beta. The angle made by this object at the objective, we call that as alpha, and the angle made by the final image, that is A double dash B double dash at the eyepiece, we call that as beta. Okay, so when you look at these two angles, this angle will be equal to this one, since they are vertically opposite angles. So I can mark this as alpha, this also as alpha. Clear, since these are two vertically opposite angles. So by definition, we have magnification M is equal to tangent of beta by tangent of alpha. Okay, now let me consider this triangle. Let me draw this in here. This is the optic center of the objective O. This is the optic center of the eyepiece O dash. We can mark this as FO or A dash. It's better you mark A dash. And this point is B dash. Okay, clearly this is alpha and this one is beta. Now we have tan beta. By definition, tan beta is opposite side by adjacent side. That is A dash B dash divided by A dash O dash. By tan alpha, this is A dash B dash opposite side by adjacent. So A dash B dash divided by A dash O. Now what I can do is, on the denominator A dash, this is the numerator, A dash O dash, on the denominator I can take the reverse, take the reciprocal and then multiply. A dash B dash. Okay, that is taking the reciprocal of this and I can multiply. This is the way I simplify this expression. So clearly these two are equal and they will get cancelled. So the final expression will be magnification is equal to, or let me write here, M is equal to A dash O divided by A dash O dash. Let me call that as equation number 1. Now I need to mark the distances A dash O dash and A dash O and A dash O dash in terms of the image distance, object distance, like etc. like that. For that, see this A dash B dash, when you look at this image, we usually represent the distance of the image as V. Since this image is formed because of the objective, I can take that as VO. And this image, the same image A dash B dash, act as an object for the eyepiece. So this will be UE. Object distances are usually measured as U. And we know the minimum distance the image should form from our eyes will be D, the least distance of distinct vision. D is actually, for normal eyes, we have D equal to 25 centimeter. That is the image should be formed at least 25 centimeter away from our eyes. Otherwise, we cannot get a relaxed view of that image. Our eyes get strained. So the minimum distance should be 25 centimeter. Any distance greater than 25 centimeter is very much okay, but the minimum distance should be 25 centimeter. Also, when you look at this VO, see, this image is formed. This image is formed from an infinite object. We know for a convex lens, when the object is at infinity, we have VO will be the focal length, FO. So if I plug in all these values in here, I'll get magnification M equal to, when I substitute all these values in equation 1, A dash O will be, see, A dash O will be, this will be FO by A dash O dash is equal to, see, this one is UE. Remember, by Cartesian system, anything which is of the left of the lens, that is this one, I have to take that as negative. So I have to assign a negative sign. See, this length is on the left of the eyepiece, so I have to write minus UE. Okay, now let me erase this. Now, if I take the thin lens formula for this eyepiece, that is, we have thin lens formula 1 by V minus 1 by U is equal to 1 by F. When I apply the thin lens formula for the eyepiece, I have 1 by, see, V is this one. The final image is formed at this much distance from the eyepiece, so that is D. Remember, that is also on the left of the eyepiece, so I have to assign minus D. Minus 1 by the object distance is minus UE. Minus UE is equal to 1 by, for eyepiece, we took the focal length as FE. So this will be minus 1 by D. This becomes plus, so 1 by UE equal to 1 by FE. So 1 by UE will be 1 by FE plus 1 by D. I took this term to the right. Call that as equation number 3. Now, let me erase this. See, when you take the equation 2, we have M is equal to magnification M is equal to, this can be written as FO minus FO. This negative can be taken to the numerator also. FO into 1 by U. Clear? That's minus FO by U itself. So minus FO by 1 by U is this one, this value. So FO into 1 by FE plus 1 by D. Okay, so this is the magnification. Now let me take this this FE outside, or it's better you multiply this FO with FE on the numerator and denominator also. Rest of the term you write it as such, 1 by D. See, this FE and FE will get cancelled. There is no change in the value. Now what I'm doing is, I'm taking this FE into the brackets. So M is equal to minus FO by FE. This FE stays here into, this will be, if I take this to the this term, it will be FE by FE. I have to distribute, so I have to multiply FE with this one also. So FE by D. So the final expression for the magnification will be M is equal to minus FO by FE into, this will be 1 plus FE by D. So this is the expression for the magnification produced by the telescope. This negative sign indicates that the image is inverted. The final image got will be inverted. Clear? Now we have to look into the image formed at normal vision. See, normal vision basically means the image should be formed at infinity. Again, I have to draw the ray diagram. Let me draw that fast. We already discussed about the final image. Now this time again, this one is the objective. This is the principal axis, and we have parallel rays coming from infinity for a telescope. So a final image will be formed here, as we discussed before. This point is the focus of the objective. Now what we are doing is we are taking this same point, that is FO, as the principal focus of the eyepiece also. We have a second lens, as we discussed before, eyepiece, and the image is formed at the focus of the eyepiece. So whenever we have an image placed at the focus of a lens, first we have to take a ray parallel to the principal axis. We have an FE here also. Let's take this as FE dash. When the ray parallel to the principal axis after refraction at this lens passes through the focus, and I have to take one more ray. This is O dash. This is the optic center of the objective. This one is the optic center of the eyepiece. All the things we discussed before. So a ray passes through the optic center, passes undeviated. Clearly these two rays are parallel. So here is our eye. So they won't meet here. So when I extrapolate it into this side, it will meet at infinity. So an image is formed at infinity. And this is called the normal vision. So that we get a relaxed view of the image. We get an highly magnified inverted image. Okay, virtual image. Now we need to find the magnification. As we discussed before, this angle is the alpha. If this is alpha, this also is alpha. See, they are vertically opposite angles. If this is alpha, this one is also alpha. And we know this one is beta. Now, see, this distance we know that is the focal length of the eyepiece. And this length will be the focal length of the objective. When I take this triangle, that is O, O dash, this is actually, let me mark this as FO, or you can mark FE. Let this point be some B. So this is alpha, this is beta. Now magnification, again it is tan beta by tan alpha. Now tan beta is actually FOB divided by, what is this length? This is FE, by minus FE, okay, since it is on the left side, by this length is FO. So tan alpha is equal to again FOB divided by FO. This FO is on the right of the objective. So you can take that as positive. So this will be FOB by minus FE into taking the reciprocal and multiplying FO by FOB. Clearly this will get cancelled. So the expression for magnification M is equal to minus FO by FE. You can transport this minus to the numerator. So this is the magnification produced at normal vision. Clear?